the recording. You did see, hello, good morning. On Google Drive, there is a lot of books and stuff I have put on O2 class. So our O2 class is up to date. There's this graded homework one I posted as well. It's more like a fresher than anything else. Very easy, straightforward. Now, solutions are available online, as you know, but the important part is for you to understand. Yes. No, we will start at 10:40. We'll start at 10:40. I just come early always. Yes. Okay, our online students haven't joined us. Not sure why. Okay. How much time? 3 minutes. And 37. Okay, I think I can just start writing. Equal to V cosine theta, and then V equal to P sine theta, and A theta is equal to A by cosine theta. Okay, 10:38. And 39. Great. I think we can start now, right? 10:39. Okay, so quick few comments. O2 classes up to date. Please have a look at the graded homework one. Number two is we stopped here. If you remember, I was struggling with making this drawing. So the whole point is that I have this simple structure, right? I hold it from here and I'm pulling it, or I'm just doing it like this. Either way, I know that when I'm pulling it, oh, what happened? When I'm pulling it, this fellow has a normal stress into it, right? The problem is that I, from my experience, know that when I'm pulling a stick, many a times it breaks in a certain fashion. If you remember, I drew that drawing in which I told you it breaks at 45 degrees. So I really am interested in finding how the stresses behave at an angle in this structure. So all I'm doing is I'm making a slice, a beautiful slice, and I really want to look at this inclined plane. That's all. So right now I am putting a load of P here and a P here, and now I'm making a slice onto it. So how should I proceed? The moment I make this slice, you can see that I have made this beautiful cut. What happens? I know that I am putting a load of P here. So according to my principles of statics, all I have to do is make a cut and have a look at what is happening on this section. I know there will be a load P, right? Straightforward from statics. I know a P is acting here. Great. But I also know that this P can be divided. Okay. Ejizan, you can hear me, right?
Yes, Ujjwal, I can hear you.
Okay, thank you. This load can be divided into two components. So you can see this green arrow. I have divided it into two components. One is this capital F and one is this V. And I think I have done overall a horrible job of making this because I don't think if you add them, you get a P. So it should be, I think this arrow should be a little longer, right? So anyways, we will correct this. The whole point is that this F plus V will give me this P. So anyone who wants to tell us which force is the normal one and which one is the shear one? The V is the shear one that is along the section and F is the normal force, right? So from here onwards, what we will do is we will play this little game. I will say that this force is P. So should I just correct myself because I don't want any student to think why these components are not adding together. So let me just make this a little lengthy and oh, come on. Or probably I should have, because you know, these things take a lot of time, but I will try my best to make it a little lengthy. Okay, now I think this is V. Okay, now this force is equal to P cosine theta and this V is equal to this load multiplied by sine theta. Now, in the last class, if you remember, I told you the formula of normal stress. So normal stress is equal to this P divided by simple area, right? This P divided by simple area, and I call it sigma naught. What I was talking about last time. Now, this time around, however, I will talk about sigma theta. This time I will just change the color. Okay, anyone who wants to tell us the formula now? Sigma theta. The normal stress on this inclined plane will be equal to the normal force divided by A theta, right? The area of this yellow section, right? Okay. Then I can say that this sigma theta is equal to, instead of force, I will substitute P cosine theta divided by this big yellow area, because of course, this area is definitely not equal to this area, right? Of course. So it is equal to divided by area. Okay, anyone who can tell us the relation between A theta and area? A theta and area. It will be divided by cosine theta, right? Everyone is with me on this? Okay, just so that everyone who has joined us, if this is the area and I'm making a slice like this, then you can see that this area definitely is bigger than this one. So this yellow area will be this area divided by cosine theta. Okay, now I will substitute here sigma theta is equal to A divided by cosine theta, and I get sigma theta is equal to P divided by A cosine square theta, right? Now what is P over A? Life was good, life was beautiful. This was P. I was pulling it. This P divided by this area was my normal stress, which was sigma naught. So I will say now the normal stress acting at an angle is equal to sigma naught cosine square. I can repeat it if you have just joined us. Do you want me to repeat this? So we started off by saying that this is the normal stress. I'm pulling it on this section. Then I said, you know what, when a structure breaks, it breaks at an angle. So I am interested in making an angle inside this and seeing how normal stress varies along that section. I drew this angle, cut it, and I drew a normal stress sigma theta and a shear stress tau theta. And I started saying what is the normal stress acting perpendicular to this inclined plane, that is sigma theta. So I started off with this derivation, force over A theta. Instead of force, I said it's P cosine theta over this. And eventually I saw that the normal stress that is acting perpendicular to this inclined plane is equal to your sigma naught. That was your original stress acting at this fellow, multiplied by cosine square theta. Okay, quick question. The normal stress that is acting perpendicular to this surface, that is sigma theta, is it larger than your original sigma naught or less than? Less, right? Less, right? So I started off by saying that I am very concerned about structure breaking at an angle, and turns out that the normal stress that is acting on this inclined plane is actually less than what was the normal stress on this plane. So let us proceed. What about shear stress? I know that shear stress is equal to, so focus on this section, please, and tell me the formula of shear stress. Oh, no, sorry. Sorry. Not on this one. I apologize, because a normal force is acting. So how can you tell me shear stress here? I mean shear stress on this yellow surface. Yes, so let's go step by step. There is a vector V along this. So V divided by the area is A theta. Then the shear stress acting on this yellow plane is equal to the V, this is blue arrow, it's P sine theta divided by area, this ginormous area, which is A divided by cosine theta. And I get shear stress is equal to P over A sine theta cosine theta. Now, what I will do is, if you remember, I started off by pulling this. There was a normal stress that is acting over this. So my only initial information is the normal stress that this surface is subjected to, the P over A, right? So I will write, instead of P over A, sigma naught sine theta cosine theta. Everyone is with me, right? So now I will just make a remark. Oh, sorry, this is shear stress acting at this angle. So let us call this as my equation 2, and let us call this as my equation 1. Now, if you look at this one, I was pulling it, right? I was pulling it, when you talk about this surface, the normal stress we know. What is the shear stress acting on this? 0, right? Are you following me? So there is no shear stress on this plane when I'm pulling it. This calculator is definitely going to break, by the way. I keep on pulling it, no shear stress. But if I make a cut at an angle, you see shear stress starts to appear. You see that? You see that, right? So definitely it makes sense that different sections are of importance to me, because right now there was no shear stress on this plane, but at a certain angles, shear stress does exist in this object. So what I will do is, I will now go to the next slide and I will make a beautiful plot. So what I will do is, should I go back? I will say sigma over, sigma theta over sigma. And then I will say tau theta over, I think there was a sigma naught. And then I will make a nice and beautiful plot, right? Let us see what happens with this plot. Are you following me? Let us do it. This is my, on the x-axis, I have a theta. So follow me. When I'm pulling it, the maximum normal stress that can exist is this, right? When theta is, so why don't you make a guess? The maximum normal stress exists when the theta is 0, right? Because as long as I'm like this, my normal stress is maximum, because all of you told me that this is sigma naught and there is a cosine square theta. So normal stress at an angle is less. Everyone told me. So I will start off by this. like this, and I will go back. If I keep on increasing the theta, cosine 90 is 0, sigma theta will be 0. So when theta is 90, it goes to a 0. Oh, what happened? Yeah. So, okay, and here comes the tough part for me. I just don't like these drawings because it's a little hard for me. So why don't you all do it yourself like this, right? Okay, so you have to connect this. It's hard for me. Okay, let's now talk about this fellow. When I go back and I see about the shear stress, everyone told me that when you're pulling it, then on this surface, there is no shear stress, right? So shear stress is 0. When theta is, shear stress is 0. When theta is, yeah. Yes. So I will go back and I will make a line like this. And when theta is 45, it's maximum, right? When theta, no, look. What I will do is I will substitute here. So when theta is 90, then the cosine 90 will make it 0. When theta is 0, then sine 0 will make it 0. But if you do a theta equal to 45, 45 is the magic number because sine 45 is 1 by square root of 2 and cosine 45 is 1 over square root of 2. So actually the shear stress will be maximum at 45-degree angle because you can do it. Theta 0 because you get it, right? Okay, so I will make this drawing. Now, I do understand. Okay, I tried my best to make it symmetrical. Now, you are seeing that here, what is the angle? 45, right? An angle 0, an angle 90. Okay, so when I have a wooden stick and I'm pulling it and it breaks at 45-degree. Everyone did attend the last class, right? Or should I make it again? So when I'm pulling a stick and I see that when I break it, it actually breaks like this. So this angle is 45. It does make sense because I see that at 45-degree angle, not only normal stress exists, I also have a shear stress that exists. But when I look at this plane, I have a huge normal stress that exists. So you keep taking a knife and keep on cutting sections like these. Normal stress keeps on existing, but shear stress does not exist. But at a 45-degree angle, yes, it is true that the normal stress, the red line, is way less than it could have existed when you have a surface like this, but you also have shear stress. So if there is any student who did not follow this, please, you can ask me, I can repeat this. If you are confused about sigma theta and sigma naught, please don't hesitate to stop me. I can repeat. Okay, let us do this again. This time around, I'm putting it like this. Again, with my experience, it breaks like this. This angle is again 45. Okay, 45. You can put a P here and you can put a P slash or again a P here if you want. The structure breaks like this. Breaks like this. Okay, so this time around, this one was P and this was again P. P or P bar, whatever, like this. Okay. Now, I do understand that the topic is not finished. We haven't even started the proper topic. In 5th or 6th, no, 7th week, we will get into Mohr circle. So in Mohr circle, you will get a complete picture. There will be a circle that we will make, and the whole task will be whenever you put load on any object, at every angle, you want a complete picture. At every section, you want a complete picture how stresses are varying. Right now, it's just a very brief introduction. I just want you to understand that when you subject an object to a loading like this, don't think that it will only break like this. It can break at an angle. Yes? Yes.
Can you explain the red line on the graph?
Yes, I can. So look, my whole point is that when you are putting a load like this, right, the maximum normal stress will be on this surface, right? Now just imagine you ask me what will happen on a surface like this. Will there be any normal stress here? I don't think so. There will be no normal stress on this surface because the definition of normal stress is that the force vector is perpendicular to the surface. So as long as you have a surface like this, life is good, maximum normal stress. You keep on increasing this angle. You keep on increasing this angle. You keep on increasing this angle and you make it flat and the normal stress on this surface will be zero. Makes sense, right?
Why in this manner we draw this graph?
Why like this? Because I went back and I saw that stress at any angle is equal to the normal stress multiplied by cosine square theta. So I, let's say, use Excel or I use MATLAB and I put theta from 0 to 90 degree and I made a beautiful plot and cosine square theta came out of that. Right? Should I proceed? Right? Okay.
And also in graph we draw the normal stress theta divided by normal stress initially, right?
Yes. So I put the denominator as sigma naught because I want, for me, the reference line was this. I'm pulling it, the normal stress I can measure easily. Okay, now comes the crazy part when I write this generalized stresses. It will really make the whole topic just a little bizarre. Generalized stresses. What do I mean by that? You know, when I am pulling this object, like this, and let's say I'm also putting a load like this, or I'm pulling this object in a random fashion like this. So there are different ways I can pull this, right? Now I can even twist it. So the whole point is that if I have an object like this, and let me draw some force vectors. This is F4. This is, let's say, F5. This is F3. And please understand that I am subjecting it to three-dimensional forces, okay? F2, this is F1. Let's make 10 more forces as well. And now I will just make a section out of it, nice and beautiful like this. So what's the point? Why I'm doing it? To get an yes, exactly. So essentially I'm using a knife to make a cut to see what is happening inside this object, and this will happen. I will have a nice and beautiful cut. Oh, Control Z. Okay. And then I will nice and beautiful. And now I am having this beautiful section. Please follow me. And now, okay, so actually I am trying to make this. Didn't do a good job, but anyways, I think it's clear. So let me quickly, okay, this is as fast as I can go. Okay, so this is the section of interest for me. And let me make a coordinate axis very quickly. And what I will do is, just for my own convenience, I'm putting the coordinate axis right through its own centroid, or center of mass, if you want to call it, to make my own life easy. This is my X, this is my Y, this is my Z. Now, here comes the crazy part. If I make a cut, right? If I make a cut and it's something is sitting right in front of me, sliced. If I ask you, what will be the normal stress? So of course, the normal stress will be like this, right? Let me use a So the normal stress will be like this. Now you can ask me, how did you come to the conclusion that this normal stress is in the x direction? Because when I made a cut intentionally. If this is the x-axis, I made the cut like this. Okay, what else would be on this surface? Anyone who wants to make a guess?
There's going to be a shear force.
Shear stress is right, because if you look at these forces, definitely there will be shear stresses. This case is not like this one. If I'm just pulling it and if I ask you what is the shear stress here, all of you told me there is no shear stress. Now there is shear stress because I have all sorts of forces that are rectangle. So let us make a shear stress like this along the surface. Let me use this color. Okay, now I have a quick question for everyone. Is this the only shear? No, right? Okay, if this is not the only one, I think there will be. Okay, let's first name this. This will be tau, correct? So this shear stress is acting on the x plane, right? Okay, in which direction? Z, right? So let me put a Z here. Okay, I will draw one more arrow and you just tell me the name. It will be a shear stress. And by the way, please don't get confused with the length of the arrows. I'm not talking about the length right now. Just let me make a random length. Tau, it is acting on the x face, right? In which direction? Y, right? Okay. Okay, focus on this stress. It is acting on this plane, which is the x plane. In which direction? X, right? Okay, I will go one step further. I will remove one of the x's. What does that mean? It means the same thing. So whenever I write 1x or 2x, you don't get confused, okay?
Yeah.
Yes.
So when you say the X plane, it means that YZ plane, right? But it's we cut
Yeah, yes.
through
YZ plane, yes.
the YZ plane.
Yes. So his question is, when you are making a cut using a knife, which plane are you talking about? It's the YZ plane and the X is perpendicular to this. In fact, just to be a little clear, I don't want you to get confused. Keep following the diagram. F4, then there is F5, so that when you look at your notes, you don't say what is happening. This is my F3. Okay, I will actually ask you a quick question. Why don't you all tell me? I used the knife and I made a cut like this, and all of you told me that stress is XX. Then you told me that there is a, what was that? Tau XY, right? Then you said tau XZ. Follow the pattern. Keep making the cuts and let's keep on going. So I will have on another face 4. What else? Yes, so 5, 6. You are right, actually. 7. Okay, I don't have space. 7. Then I have 8. Then I have 9. So you said sigma YY. Then I have sigma ZZ. Then on the sigma YY, again, I will just keep on following the pattern. Tau Y X, tau Y Z. On this plane, I will have tau Z, you fill in the blank. Tau Z X, tau Z Y. Okay, usually I don't go into such details, but I think it doesn't hurt if I add one more comment. If I remove this tau, so you understand the meaning of normal and shear stresses, right? Everyone? Do we have anyone who is not clear about the difference between normal? Everyone? Okay. Just remember that in a textbook, if you see the author doing this, and if you find it confusing, then you can forget this information. If you see the author like this, doing like this, don't get confused why the author is doing like this. This is a shear stress. Why sigma? Don't worry. Sigma xy automatically means it's a shear stress. But I think at such an early part of the course, I don't want to confuse you. So just so that you can remember the difference between normal and shear stress. Okay, what's the physical meaning? Let's see the physical meaning. Okay, you have this object, right? So I'm pulling it from here and pulling it from here. Let's say, let me put a general way, like pulling it like in this direction and pulling like this. And at the same time, I'm putting a load like this. So there are different forces that are acting on this, right? And let's say I'm also twisting it like this, some general loading. In this general loading, I will take this little knife and right through in this object, I will make a cut. I will make a cut and I will take out a cube. Okay, hypothetically, I will see that cube. On that cube, I will have all these stresses that will be available. So even right now, you can see that I'm actually taking a cut. Let me make a cube. You make a cube out of this structure. You take it out, you zoom it in, and you will see all these kind of stresses on different surfaces. Any questions till now, or it is confusing? Any comments?
Why don't we use matrices? Instead of like this.
We can use matrices. Your question is why can we?
Why don't we use?
We do. Good. We can. In fact, I will make one more drawing and I will make a matrix. Because stress is a tensor. That's an excellent comment, by the way. This is an excellent comment. Stress is a tensor. So I will, just so that all of us are on a same, stress is a tensor. We should make a matrix. You are right. So let us make a quick comment. I will make a cube. So you just have to make lots and lots of drawings here. Okay, I told you that I'm putting a load like this. I'm holding it from here. Let's call it P or P bar. Then I said, within this object, take out a cube from this object. Oh, it's just a horrible cube. Like this. I take out a cube. Then I will zoom it in. Hang in there with me, please. So I am making a huge cube, right? Okay. And as one of the students said, why don't we make a tensor? So we will make a tensor. Okay. Now you will help me. Oh, okay. We're done. So great. Okay, let's do it. This is our x-axis. Okay, this is our x-axis. Okay, I think I have not made a good cube. This one. Okay. And this one. Okay, let's do it. This is our y. This is our x. This is our y. This is our z. And okay, let's do it together. Okay, let's start making on this surface. Tell me the stresses. There would be this one. There will be a shear. And there will be another shear. This one will be everyone. Okay, the first x is this surface. That is the x. The second one, x. This one, tau x, y. This one, tau x, z. Okay, done. Then, oh, there are so many of them. Anyways, let's make this one. This one is stress on the z. in the Z. This is shear stress on the Z face in the, I think, Y. This one, Z in the X, done. And then on the top surface, quickly, this one is stress on the Y in the Y. This is Y in the X. This one, Y in the Z. Okay, done. Okay, there are 6 faces. We keep on doing it, right? Should I keep on doing it? I don't think so. Okay, probably I can do one more time. The last one. Just one more time. This one. So let's do it. We have this, then this. Okay, then this. So we have stress in the negative X face in the negative X direction. So I'm happy that we are doing this. Please put XX only. Then we have, this is acting in this direction, you know. When the right time comes, I will explain to you. This arrow will not be in this direction. We will talk about it. But anyways, so let's do it. So tau in the X face in the Z direction. And this one is shear stress on the X face.
Also, yes, the direction of the XY will be.
Yeah. Sorry, you are right. You are right. Thank you. But this is actually our next comment. But I'm happy that we are doing it. But I will explain the reasons.
What the reason is this? Newton's first law, right? Because in static case, there is an action and reaction.
Exactly.
Exactly.
Summation of moments. It's Newton's first law. Summation of moments has to be equal to 0. So I will, within the next 3 minutes, explain to you that why one shear stress on this face is upward, this one has to be downward, anti-clockwise. Then on these 2 surfaces, it has to be clockwise. So you have to give me a few minutes. But right now, I want everyone to be on the same page in terms of naming them. Okay, now I will make the stress tensor quickly because one of the students pointed it out. Stress XY, shear stress XZ. Then we have YX. Then we have YY. Then we have YZ. Then we have ZX. Then we have ZY. Then we have ZZ. So this is a stress tensor. Stress is a tensor, as one of the students indicated. So at the end of the day, I have a general loading. I am subjecting it to. I take a cube out of it. Actually, there are so many different stresses that I have to worry about. Okay, questions? Any major confusions, conceptual at this point? It's just conceptual. Okay, let us talk about few things. Now, I will spend the next 10 times telling you a story, but at the end of that story, this is what I will reach to. So I am telling you the conclusion first, and then I will tell you how to do it. So actually, this in a solid structure is the same as this. This shear stress in static equilibrium for a solid structure is the same as this one. Oh, I have to use different colors. And this, what did I leave? This one. Yeah, YZ should be the same as CY. So let us go over this quickly. So should I go over the derivation or? Okay, I think we should. Okay, just one quick comment. You can put stress equal to like this. Stress Ij equal to. Okay, let me now go over the derivation very quickly. So we have this cube. I just wish we could have done some examples today, but it's very conceptual. You have to just bear with me. So we have this cube. I took it out from the structure. Okay, let's now talk about this is stress XX. Okay, quick comment. What will be the direction of stress on the left face? Away or towards? Away, right? Okay, so in fact, I just don't want any confusions right now, so I will make this one more time. Okay. Okay. Stress x-axis is like this. What will be the direction of the arrow there? Towards right. Everyone is with me. Okay. Now, this is our XY plane. So let me quickly make, this is our X, this is our Y plane. Now, this is Y, this is X. Okay, what about this face? Tell me the shear stresses quickly. It will be, okay, a few comments. I'm talking about a two-dimensional. So I'm actually not talking about the 3D right now. So I will make an arrow like this. So it is tau X, Y, right? I'm talking about a 2D element. Please. Okay. What will be the direction of arrow on the left-hand side? Downwards, right? Are you getting my point? So tau, again, X, Y. Why it's again XY? Why didn't I write a negative XY? Because it's on the negative face. In the negative Y, you still write XY, okay? Okay, what about the direction of arrow here? So there will be a stress YY, right? Agreed? Okay, what will be the direction of arrow here? Upward, right? Okay. One quick comment. Can I do it like this? Can I do it like this? Yes or no? Can we do it? Yes. Okay. Everyone, I think everyone is getting my point. We can do it. Okay, done. Okay. What will be the direction of tau YX? Tau YX. Towards right or towards left? Towards right.
Towards left.
How did everyone figure it out towards right? No. No. So for example, why can't I do it like this? Anyone please? Why can't I make the arrow like this for tau YX?
Is it because it's tensile stress? Because when it's tensile, it becomes propositive. So it has to be in counterclockwise.
Okay, so your answer is close. It has something to do with actually these two arrows. So why can't I make the top arrow like this? We still have 10 minutes, right? Okay. I will actually make it like this and then you will answer everyone. Why I have to make arrow of tau YX like this? Tau YX like this. When tau XY is anti-clockwise, then these two arrows will be clockwise because of static equilibrium, right? Because you don't want this cube to start taking rotations. It's not possible. It's a static structure. So let me do it quickly one more time. If these two arrows are like this, what will be these two arrows? It will be opposite, right? So it's clockwise. So this will be, why? Because it's a static structure. Otherwise, there is no static equilibrium. Newton's law.
There is a torsion stress, right?
No.
Torsion stress.
No. So inside this, a cube sitting inside it cannot take rotations. This is a static structure. So that's why if this is clockwise, this will be anti-clockwise. Okay, now please remember I'm talking about a 2D element. So don't be confused. Why aren't you making the other shear stress? Because I'm talking about a 2D element. In fact, I will make these dashed lines. So in your notes, you don't say, why aren't you making the rest of the. Okay, one more comment. Can I have stress YY like this? Yes or no? Can I have? No, no, because of, I cannot have it like this. So I will just stress YY, stress YY. Okay, anyways, I think it's clear. So I will proceed. Now I will go over quick derivation. So let me make it like this. Summation of forces equal to 0. Summation of moments about a point equal to 0. So let's do it like this. Focus on the left element. Stress YY minus stress YY equal to 0. And stress XX minus stress XX equal to 0. That's why all of you kept on telling me, if this is away, please make this away. If this is away, make this away. If this is towards, make this towards. Let's talk about the second case. So I have, why don't you all focus on this one? So let's say this is our dimension A by A. So minus tau yx. I'm doing the summation of moments about this point, okay? So minus tau yx multiply by, what is the, good, area. Thank you. So I multiplied this with the area. Then I have to multiply with the moment arm, which is A by 2. This is, okay, I'm following, okay, let me, for my own convenience, please, let me just change it. Although it wouldn't have made a difference, but I am running out of time actually. So this is towards left, this is towards right, and this is downwards. You can do it other way as well. Okay. So this is clockwise moment. Then I have minus tau yx, this one, delta A by 2, right? About this center. Then I have anti-clockwise moment plus, why don't you fill in the blank for me? Tau xy multiply by this area will give me the force, right? Multiply by this distance A by 2 plus anti-clockwise moment tau xy delta A by 2 equal to 0, right? Okay, so let's finish this. I will have delta A, delta A, delta A, delta A. Okay, anyone who can tell me the answer? A by 2, A by 2, A by 2, A by 2. What is the answer? Tau
xy equals tau yx.
tau xy equal to tau yx, and tau zx will be equal to tau xz, and tau, okay, keep, what is left? Yz equal to tau zy for a solid structure. You get my point? It's just a fancy derivation. I'm just telling you, remember, tau xy equal to tau yx, tau zy equal to tau zy. So before I say goodbye to you, we have 6 minutes. Stress is a tensor. You have 9 elements. You have stress xx, stress xy, stress xz. Then you have stress yx, which is the same as xy, yy, stress yz. Then you have stress zx, then zy, then stress zz. No, it's not clear. So I will come back here. Stress is a tensor. As one of the students mentioned, 9 elements. Stress xx, stress xy, stress xc. Then yx Can I write xy or not? Can I write it like this?
Yeah.
Yeah, oh, okay. Tau yy, then tau xz, then tau zx. Can I write it xz? Yes, I can. Tau zx zy. Instead of zy, can I write yz? Yes, I can. Did I ever use it? Zx zy. This one zx. Okay, you know what? I will just make my life easy. Zx, zy, and zz. Now let's do it. Zx xz. Yes, xz. Yx, yz. Yes. Sorry, you were saying this. Yes.
Not this one, on the upper one. You wrote GG instead of tau.
Oh, sorry. Yes. Okay. You know what? If I were you, I will just write x, y, xz, yx, yz with this thing in mind that xy and yx are equal. Yx, yz, zx, zy, zz. Zx, zy, zz. And at the end, I can just write that, you know what? Tau xy equal to tau yx, and tau zx equal to tau xz, and tau, what did I leave? Yz equal to tau zy. Stress is a tensor with 9 elements. Yes.
I remember that this matrix is a special matrix. That's then those Tyx and X, Y and X, Z and Zx and Zy and Yz equal to each other.
Yes,
There
xy.
was a special solution to that matrix.
Are you talking about this tau xy equal to tau yx part?
No, I'm talking about the matrix itself. There was a special solution rather than using the normal matrix solutions.
Right now, I from the top of my head don't know. For this one, there is a special solution.
Yeah, there was.
Right now, I'm not sure, but we can look into it. But for solid structures, that's a fact that tau xy equal to tau yx. This part is clear, right?
Yeah.
But when you use the word solution,
Yeah, that has to be an equation.
yeah, that's what my point is, that we will talk about solutions to it. But right now it's just a stress tensor. So for me, you know, I'm applying a general loading to this one. If I tell you what is the situation of stress at any random element when I'm twisting it, or probably you have that board right in front of your universe. You know, this board with this rod, and there is this board for directions, right? So when wind flows over it, you have that whole rod that wants to twist, because when the air falls on the board, it wants to turn. So this rod wants to turn, but at the same time, when the wind is falling on that board, this whole rod wants to bend as well, right? So at the end of the day, if you take out any cube from that solid rod and you start to look at it, there will be in general 9 stress components. Okay. Yes.
Yes, question again.
Yes.
The reason why you said tau yz equals tau zy, because of the moments will be zero. right?
Because of static equilibrium.
Okay.
Yes.
And total moments will be zero. And because of that,
Yes, for a solid object,
for solid.
not for fluids or not for anything like that. So thank you so much.
So could we do same classes?
I thought about it. I need to contact the person who's responsible for the classes. I'm not sure whether we have a class here next. So I will shift there and then I will talk to someone.
Okay, Hocam.
I'm talking about this matrix. When these are equal to each other.
Oh yes, that's a numerical.
It's
That's
a matrix, but it is a special part so that in order to, for example,
Yes. That's a numerical, when you solve it, SOR has a name to it. What is the name? SOR? Yes. So when you have, what do you call that? Triangular matrix, upper diagonal or lower diagonal with a special property like this, you are right. Then the solution becomes very easy. But right now, there is no equation. But when we get to a point where this stress tensor has something on the right hand side, then you are absolutely right. The fact that these fellows are equal will make the solution super nice. But for fluids, it will be very complicated because, right? Okay. What is this? No. This is not our sheet. This is not our sheet.
By the way, Hocam, did you have a time to think about my other question?
Yes. So there are a couple of pages. Why don't we have a look at it? So in our textbook, there is this page, and it actually boils down to something like that is indeterminate. That profile is indeterminate. I will show you the page. We will see that. Our textbook, exactly that page talks about it. After the class, I actually had a look at it. Okay, we will.
सर एक बात आपने पूछी थी कि सिग्मा x हम सिग्मा ले रहे हैं, y के अंदर भी सिग्मा ले रहे हैं और z में भी सिग्मा ले रहे हैं, लेकिन बाकियों में टाउ ले रहे हैं.
Normal in normal stresses we do the sigma xx, sigma yy, sigma zz, but for shear stress we use the
तो हम कह रहे हैं
tau.
जब हम x प्लेन को कंसीडर कर रहे हैं तो उसमें सिर्फ सिग्मा लग रहा है, दैट इज द नॉर्मल. तो बाकी रिमेनिंग
For whenever we have a normal stress,
Yes.
we will use the
Sigma.
word sigma.
ऑलराइट.
Whenever you have shear stress, we use tau, although even here instead of the tau, you want to use sigma. It is acceptable because in textbooks and reference books, they use sigma here. But even then you need to know that with the xy or xz or yx, that's still a shear stress. You put a sigma here doesn't make sigma later does not make something normal stress. The fact that it is acting on the x face in that direction. So this is the x face and I'm pulling it. It's a normal stress, right?
This is the
my
x
plane.
face.
This is my
Yes.
plane. And I'm pulling it right
Okay.
from here. That's a normal stress.
नॉर्मल स्ट्रेस. ऑलराइट.
But if I do like this,
यस.
my hand over it, that's a shear stress because there is a normal x to it because this is an x face. But the loading I am putting on it is in the y direction.
Yes.
So that's a shearing.
Yes.
So the fact that it's acting on an x plane in the y direction makes it shear.
Yes.
The fact that I'm pulling it, it's on the x face acting in the x direction, that's the thing that makes it normal. In textbooks, that's why many times they use sigma and tau differently. But even if someone uses sigma everywhere, but with the distinction of xx, xy, xz, then you should know that xx or yy or zz means normal stresses, and xy, xz, yx, these things mean shear stresses.
ऑलराइट.
Okay, so now we have to go to the next class.
Yeah.
It's just bizarre. If we don't have a class here, why are we going to the next class?
ऑलराइट.
That's the way it is.